Hello and welcome back. Today we're going to explore a very important concept in electrostatics, electric field and electric field due to a system of charges. We already know that electric charges can attract or repel each other, but how does one charge influence another across empty space? The answer is electric field. Let's say you place a positive charge in space. Now bring another small test charge near it. That test charge either gets repelled or attracted depending on its own type. So what causes this force? It's not magic. The first charge creates an electric field in the space around it. This field carries the force from one charge to another, even when they don't touch. An electric field is simply a region around a charged object where it can apply a force on another charge. We define electric field E as E equals F divided by Q, which means the electric field equals the force experienced by a small positive test charge divided by the amount of that charge. Here, F is the electric force, Q is the value of the test charge. The direction of E is the same as the direction of the force on a positive charge. The test charge must be very small, so it doesn't disturb the original field. Now let's look at the most basic case, a single point charge Q. The electric field at a distance r from this charge in air or vacuum is E equals 1 divided by 4 pi epsilon naught multiplied by Q divided by r squared. Epsilon naught is the permittivity of free space. Its value is approximately 8.85 into 10 raised to the power minus 12. The field points outward for a positive charge and inward for a negative charge. Also, the farther you go from the charge, the weaker the electric field becomes due to the inverse square law. Now, what if there are two or more charges? In this case, we use the superposition principle, which says the total electric field at any point is the vector sum of the fields due to each charge. For example, if there are two charges, Q1 and Q2, first calculate E1, the field due to Q1. Then calculate E2, the field due to Q2. Then add both using vector addition. Since the electric field is a vector, you must consider directions. Simple number addition is not enough. You must use components and angles if needed. Let's understand with a few examples. Example 1. Two equal positive charges at opposite corners of the square. At the center of the square, the electric field from each charge points diagonally outward. Using symmetry, we combine both vectors to find the net field. This example helps build a foundation for real-world concepts like capacitors and atomic fields. Here's a quick summary. An electric field is the force per unit positive charge. It is measured in newtons per coulomb. For a single point charge, the field is directly proportional to the charge and inversely proportional to the square of the distance. For multiple charges, use the superposition principle to add their fields vectorially. Since electric field is a vector, direction is just as important as size.